Hey everyone, and welcome back to my video series on shells. I am going to talk about buffer overflow attacks today. So kind of taking shells to the next level and then showing how we can perform a buffer overflow attack. And there's other types of overflows too, such as heap, and really this diagram that you see here, you can overflow any part of memory if you wanted to, but we're going to focus on the stack today. That's the most common type of buffer overflows. So I'll post this in the video chat, but or the video comments, but basically this is a piece of memory, and if we count, we see 1, 2, 3, 4, 5, 6, 7, 8, right? And it's represented F, so we go from 0 to all Fs, and this is hex, so that means there's going to be 4 bits to each of these. So this is a 32-bit stack, or not stack, but memory. Um, 8 times 4 is 32, right? So looking at, this piece of memory, we can see the OS kernel space. Um, and this is basically just where kernel commands take place. We got the stack, which is variables local to a function scope are stored, and that will grow downwards towards lower memory addresses. Then you got heaps, so you think like malloc and other types of methods in C that will allocate heap memory, and that will grow towards higher addresses. And then we also have BSS, uninitialized static variables filled with zeros, data, static variables explicitly initialized, and then text. This is like basically where the actual code resides for a program. So this is kind of a good overview of stacks. I'll post this in the resources, but I wanted to show how to basically create a buffer overflow exploit for Buff on Hack the Box. Um, and kind of continuing on from the last video, so let's just grab my IP really quick. Okay, so that's my IP. If I um, if I let's see, let's go here. Okay, so we got our exploit and we renamed that to gem.py. And yeah, I did cheat and I basically tried this exploit already. I have a guide and you'll also get that in the resources. But gem.py, that was our initial exploit. So if we go Python 3, well, let's look for Python 2.7 first, right? Because if we recall, gem.py, we would run this exploit on Python 2.7. But I'm using the Parrot OS, which only has Python 3. So I can like say which Python 2.7, nothing's returned, 2, nothing's returned. But I do have 3. Okay, so let's just go ahead and run this with Python 3. Gem.py. I'm trying to remember how this exploit works. Put in our IP address and okay. So yeah, I did modify this exploit. Um, and it looks like we're intercepting it here in BERT. So let's go ahead and forward that. Okay, yeah, it looks like I need to do some modification here. I'm going to pause the video quick. Alright, so that gets me every time. So basically what I forgot to do is add this slash, and that's why I got an error back, because that wouldn't be the correct path. So adding that slash, the exploit continues on. So here's our payload. We'll change this to request. We'll forward that, and we'll forward it, and we'll see that we got a web shell, except we didn't because it exited right away. Okay, but it did deliver our payload successfully, right? So if we look at, you know, if we look at burp, Let's go back to burp. If we look at our HTTP history, it looks like we were able to deliver this successfully, and it looks like we're able to run a command off it. Yeah, so this is a command, and we're able to run this successfully. So if we send this to repeater, and if we just try like another command like who am I, we'll see that we're getting results returned. So we could basically use this payload and probably get a shell. And what I'm going to do is I'm going to follow a guide where like an SMB server is set up, and then we basically host a netcat executable, and then we execute that xcat executable um, through SMB by copying it on to the server and then running the command. So to show that, let's go into our folder where we host files, and then here we see NC64. So we could set up an SMB server here. So let's go ahead and do that. Well, let's try to locate where our SMB server is first. So SMB server pi, because I'm not familiar with Parrot OS. Okay, so it looks like it's here. So let's just go Python. And I apologize, I'm not the quickest typer. That's why I like to prepare my videos ahead of time. Um, I fat finger a lot of things, and I'm kind of a creature of copy and paste, so bear with me. But we're basically setting up an SMB server using Impacket. We're creating a, a, a folder like SMB share TMP, and then we're going to put that in our current working directory, and then we're going to enable SMB2 support. That didn't work. And it didn't work because I think I used the wrong one. So if I go here and then delete this and then use this guy instead, Impacket. Got an extra space there too, don't I? Okay, now let's try it. Okay, that worked. Okay, so we have an SMB server and we have command execution in Burp Suite, so we can then set up a listener, right? And then we could say do this over port 80. And Parrot's different than Kali. This requires privileges to be ran. Okay. I apologize. I might have to pause the video. This is the first video I've done where I'm doing an in-depth subject, such as buffer overflows. But basically now we have a SMB server and we have a listener. So since we have command execution here, we can basically copy this netcat file. So this netcat file under www, we can copy that onto the server and then execute it. So to do that, we'll go to our, and I think I'm 0.5, and then we're going to go to our SMB share, and then here's our executable. And remember from last video, we determined that this is a 64-bit machine. I'm messing something up. No, that's right. Okay, so we'll execute command prompt. And then I could do a URL code in this and just do spaces, but I'm just going to put in the plus. And then when I send that, hopefully it hangs. It looks like we're connecting. Okay, so connecting to the share. Might take a while. There we go. All right, so we got a shell. So we basically set up an Smb server. And then since we had command execution here, we were able to grab that NC file and then execute it and then get our shell that way. So now that we have an Smb server, we can basically upload files to this machine and download files, and that's great. And then so if we go here, and then let's just look at our users. So dir. Okay, we have our user Sean, so let's go to Sean. And we could just basically be navigating around, exploring. Let's go ahead and check out the downloads folder. So if we go to downloads, and then we go dir, we'll see that we have this CloudMe executable. And some quick Google searching, you'll find that there's actually an RCE for this executable. So like if you just did a Google search on this, um, like this, and then you could just say exploit. What is going on? That is slow. Oh, I need to get rid of this. Take intercept off. Where? What happened to Firefox? Okay, so if we just do a search for this, come on. I guess I gotta pause the video again. I'll be right back. Okay, sorry about that. I'm just gonna look for it here. Um, I don't know why my machine's locking up. But yeah, just doing a simple Google search, we can see there's an RCE for this, matching this version. And that looks to be the version that we have here. So 11.12, and this looks to be good for 11.2. Or yeah, 1112. Yeah, that looks to be the exact version. Okay, well that's great. So we could use that exploit, but I want to run through writing a buffer overflow exploit from scratch because I think it would be good practice. So to do that, we first need to copy this down onto our local machine. So since we have an Smb server up, we could basically copy this like this, right? We could go that, and then we actually, well, we have it in our clipboard. So if we just do .exe, and then if we just say to our machine, and then to our shared directory, and then we'll just call it cloud.me, right? .exe. And this might take a little bit. All right, so That took a while. And it's asking if I want to overwrite it because it already exists. So I'll just say yes. And the pause button on Snagit is great because it allows me to snip out all the boring parts if I need to. But we see that our file has successfully copied. And yeah, so now we basically have this file on our local machine. So if we go to our machines, buff, ww, we have a file here. And I'm going to disconnect from Hack the Box because for some reason when I'm connected to it, it uses up just a bunch of networking traffic. And I'm not sure if like someone's trying to mess with me. I hope not, but I changed my IP and everything. But yeah, I for whatever reason it's being a pain. So we basically got our uh, application, our vulnerable application on our computer, and now we're just going to close down this window because those are no longer valid. Um, okay, so now that we got that on our local machine, we can basically write an exploit. And I got a lab environment set up just using Oracle VirtualBox. So if we go to just here and just type in ifconfig, we'll see that I have an Oracle VirtualBox set up where this is my IP for Parrot OS, and then bringing over my Windows machine that I had set up, IP config. This is my IP for my Windows machine. So I'm going to be swapping back and forth between the machines. I don't have a really good video editor. I'm just using a basic version of Snagit. Um, but yeah, basically, I have my own little lab environment. And normally I would have this like my Windows machine DMZ'd. It'd be like a vulnerable version of Windows, right? Um, or I'd be running vulnerable applications like CloudMe, which I've already installed. Um, and then I'd be like tunneling into it through a VPN or something. But I don't have my server set up yet, so I don't have that environment quite yet. I'll probably post a video on doing that sometime. Um, okay, so I cheated, like I said, several times now. Basically, I just have this exploit shell set up, right? And we could basically do all of this just using the socket library in Python. That's why Python's such a great tool for developing exploits. It has a lot of libraries, and it even has like I believe it's Pwn tools, and I'll have to do a video tutorial on that sometime, but it has like frameworks in that for developing exploits. So I have the IP of my machine in my lab, and then CloudMe generally runs on port 8888, and we can verify that by basically pinging, or not pinging, but doing an nmap scan on that port, right? So we could go nmap 10.0.2.20, right? That's the name of this, or that's the IP address for this server. I always get confused. 10.0.20. Yep. And then I could just say port 8888, and then let's go ahead and grab the banner for that, and we'll just hit run. And it comes right back with Sun Answer Book. So yeah, there is a port open and it's listening on that. It's identifying the service as Sun Answer Book. I think a little bit of digging around that service will show you that it is in fact CloudMe that's running. So we know that vulnerable program is up and running on my Windows machine. So let's go ahead and try to write a buffer overflow exploit for it. So normally you would start off with a fuzzer. You just have a while loop and then you would increment it um, by like 100 characters or so. Let's just give it an arbitrary number of like 2000 characters, right? So if we go back to our Windows machine and if we open Immunity Debugger, And I'll post directions on how to install Immunity Debugger in mona.python. Um, but basically, we'll just open Immunity, go attach the CloudMe service, hit attach, and okay, we see that it's paused. So there's our status down here, which tells us what the program's doing. And since it's paused, we're going to hit run. We could also go to debug and press run or just press F9. And it looks like it's running. Okay, so that looks like that's stable and it's executing. So let's go ahead and save this payload. Let's open up a shell. And then let's just go Python 3. Well, first we got to navigate to it actually. Is it in Buff? No. Okay, and this is CloudMe, right? Yeah. So we'll just go Python 3. Well, let's go over this exploit first before I even do that. So I'm importing socket. I have host and port defined. Yep. Got a definition, and I'm basically passing in a parameter build size. And then I'm returning a bunch of A's. So whatever I pass into this parameter is just going to return a bunch of A's multiplied by that size. Um, and then using the socket library, this is how you just open up a TCP socket. And then we're setting up a timeout of 2 seconds. And then we're going to try to connect to the host. And then we're going to send our payload, which is basically our build, right? So then we're going to, in a try catch, try to send the payload. And if we fail, then we basically get a timed out error. And then here's our main function where we actually use those two definitions above. Okay, so we're going to try to send our payload. me.py. And we see our payload was sent successfully. And if we go to our Windows machine, we see that the ESP is overwritten by a bunch of A's. And I think that was one thing I forgot to go over is that, okay, so in our memory, there's a bunch of these registers, right? And our goal is to basically overwrite the stack pointer. So what is the stack pointer? In this guide, stack pointer is basically a pointer to the instruction that the program is currently executing. So, and then I believe was ESP, which is always pointing to the top of the stack. So I think our goal, or I shouldn't say I think, I know our goal is to basically have this point to the top of our stack where we could basically put a malicious payload, right? So that's the whole goal of buffer overflows, is that we're basically going to point to our payload, the start of our payload, or probably give ourselves a few no-op sleds or a few no-ops to basically tickle on until we hit our payload. So it's basically a sled that, and you'll see what I mean here in a bit. Okay, so we basically overwrote ESP with a bunch of A's and all of our registers with a bunch of A's. So we know that a payload size of like 2,000 characters is going to crash our our program. So what we need to do now is basically determine when we start to overwrite EIP, and that's where Mona debugger will come in. So if we go and type this command, so there's a command line down here, Mona, and then PC for pattern create 2000, and if we hit enter, that's going to bring up this log window, right? And then it said that it created a pattern, and then it warns you, don't copy this pattern from this window because it's truncated. So we got to find this pattern.txt file. So by default, when you install Mona, it's in this location. So we'll go here, users, your username, app data, local virtual store, program files, immunity incorporated, immunity bugger, and then here's our pattern. So this is our pattern of 2000 characters, and we're going to just copy that, and we're going to basically paste that into our exploit. So that's going to go here, and we're not going to multiply this by size because this is 2000 characters. Okay, so we have our 2000 characters. Let's go ahead and return this pattern. And let's set pattern equal to this. So we'll go ahead and save this, and then we will send the exploit again. Oh, but before we do that, let's restart our program. So this log window popped up. We can basically just minimize this, and then to get our view back, we'll just expand this CPU registers, or this CPU, which shows all the registers. And then if we go debug, restart, and then we can look down here and it does this analysis. This takes a little bit. So this will probably be a longer video today. I apologize for that. This is a complex topic, and I'm learning buffer overflows myself for the OSCP. So yep, we got a pause state. So now we can basically run this again. Okay, so we'll let it start up, give it a little bit. We'll close this, and it looks like it's in a stable state. So we'll send our pattern. Okay, payload was sent successfully. If we go over to Windows 10, looks like we crashed a program, and it looks like EIP was written with these characters. Okay, so what we could do is we can copy the selection to clipboard, and then we'll go to pattern out. I think that's what this stands for, pattern out. And then we basically just put in these characters, and it's going to find the offset for us. We'll hit enter. Pattern offset is at position 1052. Okay, so we need 1052 characters before we start to overwrite the instruction pointer for the stack. And once we overwrite the instruction pointer for the stack, we can basically then point it back to ESP or wherever our malicious payload begins, right? So if we go here, and so now that we got our offset, we basically need to modify our payload. So what we'll do is we'll go and add another set of parameters. We'll just call this junk. And then this will just be A. And then we have an offset. So let's go offset. And then I'm going to pause the video because, like I said, I'm a terrible typer. So I'm just going to basically make the changes and then I'll go over them. Okay, so I made the changes to the exploit. And you'll probably see it from when I pause to when I resume the video recording. But I basically added a new parameter called offset. And this is where we can pass in like our 1052 characters down here. I created a variable called junk. This will just be a bunch of A's times our offset. So like I said, we're filling it all the way up to with junk to the EIP register. And then from there, we'll overwrite and make sure that we're overwriting this with B's, which should be hexadecimal code 42. A's are 41, B's are 42. And then after that will be our shell code, right? So that'll be hexadecimal 43. And this will just be times like whatever's left of our 2000 characters, right? So we're passing in 2,000 characters to crash the program. It'll just be 2,000 minus our offset of 1052 minus the length of this instruction pointer will be where our shell code can go. And that's going to basically be our payload. Um, and then we're going to basically assert that our payload is equal to the size that we're passing in. So that's the beautiful thing about Python. This will fail, and then we'll know that we did a calculation wrong somewhere. Python is great for exploit development, like I've said. And then return our payload. So that was the changes that I made. I'm going to save this, and then I'm going to send this payload again. Okay, so it says that it timed out, and that's because I did not start up, or I did not reset our program. So I'll just open up the CPU registers again, go restart. Okay, and it's paused. Looks like it's ready to run, so let's go ahead and run this. Wait for it to get to a stable state. So it looks like it's just starting up things now. We'll just close it, and it looks like it's in a stable state and that it's running. So if I run this exploit again, payload was sent successfully, and we should see EIP overwritten with a bunch of B's. And we do. Great, so it looks like we're able to write to EIP now, and then here's our payload. So if we go down here to this window, we see all of our junk basically, all of our A's, and then we see our B's, and then this is where we could basically put our shell code, or we could put some no ops here and then our shell code. Okay, so since we are able to control EIP now, we need to find a place to where we could jump to a function or module within our program to basically execute our shell code, right? So there's something called ASLR, and there's also DEP and other basically protections on the operating system that will prevent buffer exploits from happening, right? So we want to find an area that we could put our shell code that won't have these protection factors. And with Mona, there's a way we can do that. So we can, again, go to our command line in Mona, type ASLR, or no ASLR. If we hit enter, brings up our log window, and this basically gives us all of the modules or DLLs that don't have these protection mechanisms. So like here, this wouldn't be a good protection mechanism. So we have a few to choose from. I'm going to use this guy here, this qt5 core.dll. So I'll go Mona, and then I'm going to say jump. I'm looking for a jump instruction. And then in reverse order, that's what this TAC-R does because we're dealing with Little Endian because this is an Intel processor. So Little Endian means that when I look at an address, it's going to basically be put out backwards. And I'll show you what I mean here in a bit on that. But basically a jump instruction to ESP in this module, qt5 core.dll. Okay, and it looks like it found it. Okay, so for some reason it opened up the CPU window, but if you go back to log, here it finds the pointers, and it basically put these in Little Endian order. So 68D652E1, we can just choose the first one, and that's going to be where we're going to have our EIP overwritten, right? So to show you a little Indian order, let's go back to, okay, so first we need to basically copy this. So let me make note of this. And if we go back to parrot, our EIP is basically going to be put in little Indian order. So that means since this is, if I just do a comment here, 0x68D652E1, I'm going to put this backwards. So we'll get rid of this multiplied by 4, and in hex we'll go xe1 slash x52 backslash x stands for hexadecimal slash xd6 slash x68. Okay, so that's little Indian order. It's basically this backwards. And that's how we gotta enter in our EIP. I'm gonna make some more changes to our shellcode. I'm gonna pause the video and then I'm gonna come back and explain it. Okay, so I made the changes and you can see I modified the shellcode. So I basically filled it with XCC, which really isn't any characters that I can see in the ASCII table. You'll kind of see the characters that come out from that, but that basically shows the start of our shellcode. And then junk2, which basically does a calculation for the rest of our shell. And I think I missed something. Did I miss something? No, maybe not. Okay, so I added junk2, and now our payload is basically junk plus EIP plus shellcode plus junk2. We assert that our payload is the size that we're passing in, and then we basically return our payload. So that's the changes that I made to the exploit, and now I should see EIP overwritten with this. So I'm going to go back to Windows and restart the debugger, or restart my program. So if I go restart, give it a little bit. Okay, it's paused. Let's go ahead and run, wait for it to get to a stable state. Okay, so it looks like it's in a stable state. So let's go ahead and send our payload. Just clear this out. Looks like payload was sent successfully. And we have our program terminated. And our EIP is overwritten with this address. Okay, I apologize about that. I was a little unsure on what I was seeing down here, so I had to look at my OSCP guide. But basically, the reason why we got this is expected. Um, this bottom view here is the stack, and this shows the hex data that is residing at that address. So we're seeing that here, and then we're seeing that, yeah, we're basically returning to QT5 core. So we're basically jumping to the start of our payload. So that's why we're jumping to this address here. So 00A3D3D1, 00A3D3D1. So hopefully you see that. Hopefully you see that basically by filling the EIP, we're jumping to this address, which again allows us to jump to the start of our payload. I apologize, I can go over this probably in more detail later, but right now we just kind of got to move on. So we basically found a spot to where we can jump to the start of our stack, ESP, which would be the start of our payload. Now we need to check for something called bad characters. And the way we can do that's really quite easy. So we can basically, with MonaDB, if we go byte array, And then this, I can't remember what the definition for this tag is, so I will just find it. This is basically an option that allows us to specify bad characters for pointers. Um, so right off the bat, X00 is a bad character, right? Um, no matter what, I mean, this character is always bad, usually in buffer overflows. So if we go ASCII table and look at what that character is, um, it's just a null character. So null characters are generally always bad in buffer overflows. So using this command for Mona, let's go ahead and run this. Okay, and here we get all of our characters. And we wrote it to this file byte array.txt. So that's in the same location as our pattern.txt. So if we go byte array.txt, we can basically replace all these characters. So this is just the whole entire hexadecimal range from x01 to xff is what MonaDB generated for us. It looks like I got a couple of these open. Okay, so if I minimize this guy, and then if I replace our payload with this, so like if I go shellcode plus equals, and then we'll just do, so it'll be byte. Don't think I need that. Yeah, I already got that in here. So go B, and then I'm gonna pause the video quick. Yeah, so I basically just appended to our shell code after this XCC all of these characters. And now Mona is going to help us figure out which one of these are bad. So if we go and save this, and then if we restart our debugger, so we'll go restart, and then, okay, it's paused, so now we can run it. Wait for it to get to a stable state. Okay, so it looks like it's running. If we then send this payload, we see that this has crashed, and it looks like this is where our payload starts. So Mona's got this great command that basically will compare it against the byte array.bin if you just put in this address, and from there it determines all the bad characters for you, so you don't have to do that manually. So the command for that is Mona compare, and then tact f, which can't remember what tact f does. If I look over here, I'll post this in the link or in the references. Um, yeah, I'm not exactly sure what all these commands do. I'm just kind of following this guide, but tact f, and then if we do the path to our byte array.bin, which is here, so we could go properties and then just grab that path. Let's just do this. And then I think we'll want to put this in double quotes. And then okay, so that's good. So then we need to do byte array. I told you guys I was a terrible typer. And then if we go tagged A, which again, I'm not exactly sure what that is, but basically it's going to be this address here. So if I copy this to clipboard, and if I just use that address, it should determine what all the bad characters are. So it brings up the log window, and it looks like we don't have any other bad characters other than x00. Okay, so we determined our bad characters, and now we can basically generate our payload. I understand this video is getting quite long. It's probably a bit choppy because I've been pausing as I try to troubleshoot on what exactly is happening, but I'm going to basically switch over to the exploit that I've already created. So if I go File, Open, and if I go cloud.py, I'm basically going to generate this payload, and then using MS Venom. So here you see that this is the bad characters that I used. I'm putting it into the format Python, and then I got my local host machine, my port, and then I'm using Windows Interpreter reverse TCP payload. And what that does is it generates out this buffer. So then the only changes I need to make to my payload are adding this buffer to my shell code. So looking kind of back at here, this XCC, we're going to create no ops for this. And like I alluded to earlier, no ops are basically no operation is what it stands for. It's going to tick along. So if our EIP that we point back to ESP somehow lands like a little bit before our payload, it'll just tick along in what we call a no-op sled until it hits the beginning of our payload. So that's the whole point of no-ops, is it basically gives us some wiggle room to execute our exploit. So this is all done, and then there really isn't anything else that was modified in this exploit. This just was, hey, successful, payload sent successfully. And yeah, that's about it. That's going to be our buffer overflow exploit. So I'm going to save this and I'm going to run it. And this is cloud.py. Okay, so instead of, so hopefully you see that. Hopefully you see that I just ran this command, put in this buffer, and then replaced those with XCC with no ops, and then added this buffer payload. I'm going to go ahead and run it and show you guys that I can in fact get an interpreter session. Okay, so we'll go debug, restart. Okay, and then I'm going to run it. Wait for it to go through its startup. Okay, looks like the program started. So now, before I even do that, I am going to use multi-handler. So let's go start up MSF console. And then let's go ahead and split this screen horizontally. Okay, so it's cloud.py that we'll be using. So I'm going to search for just multi, see if I can't find the multi-handler. Actually, let's just search for handler. That'll be easier. Let's go search handler. Okay, so yeah, 30 is the one that we want to use. So we'll say use 30. And then if we go options, we see our payload is generic shell reverse STP, we actually want to replace this with the payload that we're using in our exploit. So let's copy this, and then we'll say use payload, or no, is it set payload? Yep. Okay, so now we have our payload set, and we are going to want to listen on 9968 because that's the payload that we generated it for. So let's grab this IP address. Clear. We'll say set L port to 9968, and then we'll set our L host to our IP address. That looks good. Let's go ahead and run this. Okay, and now we started a handler. So now we should be able to send our exploit. Payload sent successfully, and we got an interpreter session. So I should go into staged and non-staged payloads later. This is a staged payload, and what a staged payload is that you basically send like part of the exploit, and it creates like a connection, and then once that connection is established, you send the rest of the exploits. So they tend to be, I want to say they tend to be smaller than like the non-staged. Non-staged would just be this underscore, but um, they're a little bit more stealthy, and that's part of the reason why I love interpreter sessions, is that you get all these options, and then eventually we'll go over encoding. So I do apologize for today's video. I'm sure it's a little bit choppy. I had to pause at a lot of points. Like I said, I'm still learning buffer overflows myself, but I hope to cover like heap overflows and other overflows. The next video series I'm going to do is going to be on local and remote port forwarding. So we're not quite done with the buff machine yet. That's still going to be a great machine to demonstrate that. I have also started a new position, so I might be a little bit sporadic in posting my videos, but I'll continue to post to this YouTube channel, and if there's anything that I miss, or if there's anything that I could have done better, let me know and I will redo the video or explain in the comments. So with that, we're 53 minutes long. Thank you for staying with me through this, and hopefully you now know a little bit more about buffer overflows.